Welcome to this presentation on understanding design of experiments, one of the key tools within the Quality by Design framework. My name is Mattias Arnfeldt. I am the Six Sigma Master Black Belt within the biotechnologies business. This is the outline of the presentation. We're going to be looking at an introduction to design of experiments, then moving into examples of some different experimental designs typically employed within DoE. We will then talk about evaluation of DoE data using a very simple application note on optimization of dynamic binding capacity on the capital S resin. The evaluation part there is divided into two parts. First, evaluating using a full factorial design, and then evaluating the dynamic binding capacity data using a central composite phase center design. And finally, we will look into going beyond the DoE-only approach, applying Monte Carlo simulation to DoE-developed transfer functions models to enable a probabilistic process design. The presentation will be split up into three parts, where today we will be looking at the first two bullets on this slide. So what is really design of experiments all about? Design of experiments deals with quantifying how process inputs affect process outputs using a minimum number of runs. So if we consider a unit operation like in downstream processing, typically we would have some input factors, so parameters coming into the process from, let's say, a previous unit operation that has an impact on the process outputs. So those would be the Z factors in the cartoon to the top left. We would also have a number of in-process factors within this unit operation that we're optimizing and trying to understand better, number of factors that we can control within our unit operation. Those would be the X factors on the cartoon. And we would then measure a number of different process outputs or responses to our system to describe the quality and the economical performance of our process. So DoE deals with quantifying how those responses depend on the process inputs. The nice thing about design of experiments is that it does so very systematically, allowing for detailed understanding of how the cause and effect relationships look like, and it also does that in a minimum number of runs. So by employing a structured design of experiments approach to our experimental efforts in process development, we can arrive at a detailed understanding of how our processes work in a much shorter time than by employing a more random or one factor at a time approach of developing our processes. So if we look into a couple of different reasons, more technically, why design of experiments is a good idea. The first reason is that if our process has interactions between our process inputs, we really need a DoE approach where we systematically change all our process inputs, or the key important process inputs, simultaneously, to be able to quantify and understand how those process inputs interact with each other. If we change one factor at a time in our optimization efforts, we will never learn if the effect from the parameter we are changing is affected by the setting of another parameter on the input side. So one factor at a time never discovers if we have interaction effects. But we do that with a DoE approach. Second reason for DoE is from an interpretation perspective. If we consider the two cartoons at the bottom of the slide here, the cartoon at the left pictures a one factor at a time approach to optimize or investigate in a three-dimensional parameter space around the red center point. And you can see that we are changing in the XYZ directions, one direction at a time only, going to the different green experiments, green points there. So you can see, of course, that we never approach a corner point of our experimental space, and in effect, we don't even cover the three-dimensional room where these three parameters will live for our process. On the right-hand cartoon, we have what a full factorial design in 3 parameters look like. And as you can see there, we have 8 experiments, each in a unique corner point where all the x parameters are set either at a high value or at a low value simultaneously. And that enables the quantification of interaction effects, and it also means that whatever statement or knowledge we build about our process around this red center point, we will have covered that space with our corner points from the factorial DoE. Thirdly, the third reason for DoE has to do with random noise or process variability, which truly is a very important aspect from a manufacturing perspective, because it's not only about having the best set point for the process, it's also about quantifying how much random variation we should expect around a locked down process or a sweet spot for our processes. So with design of experiments, it actually enables the experimenter to use all the experimental runs that we make. All of those runs can be used also, or are used also, to quantify this random variability of our processes. So of course we use the experiments to quantify the cause and effect, but we also use all of the experiments to quantify the very important random variability that our processes has. And finally, this all boils down to that if we look at it from a time-cost perspective, design of experiments really requires a minimum amount of resources considering the amount of information and knowledge that is built in our process development efforts. And this is especially true when the number of input parameters and process parameters increases. So some basic DoE terminology. We talk a lot about factors in design of experiments. So the factors are the process X's or the independent variables, that either a factor is something that we can control within the unit operation, or it is something that we really cannot control, but we can measure it and we can quantify if it has an effect or not by following a structured approach if we cannot control it, we can still perform experiments when this uncontrollable factor is high versus when it is low. If we think about it like seasonal changes in temperature or humidity, we cannot control the weather, but we can quantify the effect of weather by performing structured experiments when we have a very high temperature with very humid air versus very dry and cold air in the winter. So even uncontrollable factors can be quantified using DoE. In addition, on the factor side, you would have typically process outputs from previous unit operations or properties of raw materials for the unit operation we're looking at. Those would also be factors potentially impacting the output of our processes. So the output of the process or of the unit operation in DoE is called a response. So depending on how we set our factors, we'll get different responses from our process, different outputs. The model or transfer function within DoE is the mathematical polynomial that quantifies the cause and effect relationship between the factors and the responses. So the model or the transfer function quantifies how the factors affect the responses. And finally, the experimental design is nothing more or less than the actual experimental runs that we do. So we can either make a larger experimental design, so more experimental runs, which will enable us to use a more complex, more detailed model transfer function. And that would be needed if there is a very complex behavior of how the factors affect the responses. Or we could make a more lean approach to experiment, number of experiments we do. If we do as few experiments as ever possible, we're going to be able to maybe only fit a linear model. So we would not be able to maybe quantify interaction effects or curvature and so on. So experimental design, we have a range there of how many experiments we use, and that connects directly back to the model transfer function, how complex polynomial will we be able to fit to our data. So this slide summarizes a number of factors and responses in chromatography. It's not an extensive list with everything that could ever be changed or could potentially have an impact. And also the list of what you can measure on the response side could also probably be extended. But this is a little bit humbling in terms of it's really rather complex how to optimize and develop a chromatography unit operation. At the same time, we should never forget about the previous knowledge we have of our unit operations. And also we should if we go into DoE for downstream processing, we shouldn't forget about the value of a gradient run, for instance, to learn about how our protein purification process responds to a pH or a salt shift. So both previous knowledge and scouting runs can perform very valuable information about which factors on the factor column there are likely to be important and really important to discuss, to investigate in detail, and can help a lot. Also previous knowledge, we will know typically a lot about the resin in question, how that normally performs on different kinds of proteins that we want to purify. So within design of experiments, we talk about three different objectives for our investigations. And if we think about those three objectives also versus a timeline in process development, we can map them as process spaces as well. So starting out early in process development, we're not really sure about which factors are the most important ones and in what range we are most likely to have the best process performance. So in this early scenario, we would turn to screening DoEs, typically, where the question we ask us is which factors are important and what are the appropriate ranges for those factors. So in screening DoE, we don't necessarily aim for a detailed predictive model, but more want information on whether we should go left, right, or carry on straight ahead with our process development work. Also a comment about screening and early stages of process development. Since the availability of the HDPD formats, like multi-well plates or these super small columns, a lot of the downstream screening can be performed in those formats, which really helps the column format or the bigger column format investigations to quickly move into the second objective instead, which is optimization. So when we perform an optimization DoE, we have already identified the most vital factors, the most important factors, and we know approximate ranges for those factors where we're likely to have a good process performance. So in optimization DoE, we ask the question, what are the optimal ranges for those factors? Where do we really have the sweet spot for our process, considering all different process outputs or responses that we need to consider for our purification process. So in optimization, we would typically need a rather complex DoE polynomial for the transfer function or the DoE model. So we would have a rather complex model, meaning we benefit greatly from having reduced the number of X parameters or responses that we study. So think of it like a funnel with many possible parameters in the screening, and we then screen away the non-critical ones to really identify the most important parameters for this particular unit operation, and those we study in detail using optimization DoE. That would lead us to understanding then where we have the design space, which under QBD is defined as the design space is the process space where we have a reasonable, an acceptable assurance of quality and a quantified and acceptable risk for our processes. So basically, within the design space, everything is okay, and we would employ the optimization DOEs to quantify that. Final objective within DOE would be, classically, would be robustness testing. So in robustness testing, the question we ask ourselves is, is my process robust to small variations on the process inputs around a particular set point? So if we think about an optimization DOE to tell us in detail how a process works and what the cause and effect relationships look like, we would then, in the evaluation of the optimization DOE, arrive at a suggestion or several suggestions about where we have a good process performance. Naturally, the next step is to verify that conclusion. And also on a process development timeline, we would encounter a scale-up sooner or later, definitely a scale-up also, where again, verifying that the conclusions from the smaller scale is valid also in the larger scale. Robustness testing DOEs are very useful for that purpose, for the purpose of addressing those questions. What robustness testing DOEs do is that they again use a very low amount of experimental runs in a rather large, if one likes, a really large number of process X parameters, but very few runs, with the aim of just checking that the results are okay. So do we get approved purities and impurity profiles and acceptable yields for our process around the sweet spot from the optimization DOE? So we're not trying to build a new predictive model or develop a complex transfer function when we do robustness testing. We run a few experiments in a structured way to make sure that the conclusions and indications we saw in optimization are indeed correct, and also that we have a scalable, nice, transferable process over to manufacturing. We already talked a lot about the models and the transfer functions, and this equation here is the classical way to describe in a simple equation how design of experiments or regression in general breaks up the observed variation in our experiments that we perform. That would be the Y. That's the total variation we see in our experimental runs. We break it up into two parts. The first part being the f of x part, representing the transfer function or the polynomial model in DOE that quantifies the cause and effect part. So quantifying how the systematic variations in the process inputs that we have performed in our experimental design connect and affect over to the response on the process output side. So that's the cause and effect part, that's the f of x. And what remains, what the model cannot explain, then resides within the error part, the E part in this equation. So that's where we have the prediction errors or the residuals. And that's also where we get now the quantification of the random variability in our processes. So think about it, if we have zero variation on the input parameters, that's the X part, and the f of x will not change, but we will have some random variability in the error part, typically due to measurement system variations and also, now, of course, the process random variability in itself. So about some model details for the DOE polynomials, if we consider a response y depending on two process inputs, x1 and x2, there's a three-level hierarchy for the complexity of the DOE polynomial or polynomials most typically employed in design of experiments evaluation. Starting from the left, with the left cartoon, if we start out with only a linear model in x1 and x2, we get response surfaces or describe the process as a horizontal or as a plane, a flat plane oriented somewhere in the multidimensional space. So that would be the most basic, the most simple model, and the one that we can have a good statistical support for in the least number of experimental runs. Adding one more level of complexity would be to go to the the middle cartoon, the middle response surface, which adds an interaction effect between the two process inputs, the two x's. So if we look carefully on the middle response surface, you see that in the front end of the picture, you can go from left to right and all the time be in the blue region. So the height here of the curve of the response surface, or the color, that's the response we get from the system. That's the value of our response. So we have more or less the same value of our response, no matter if we go from left to right in our x1 parameter. However, if you go to the back of this middle response surface, you'll see that the same change going left to right now implies a drastic increase in our response. So changing the x2 parameter from being in the front of the picture to the back of the picture changes how the x1 moving from left to right affects our response. That's an interaction effect, and we will exemplify that again in slides to come. And finally, going to the full complexity of a DoE polynomial would be to also add second degree curvature. That's what comes at the right-hand cartoon or response surface. So this is adding x1 squared and x2 squared to the polynomial. And that enables the DoE model to either describe a maximum, a minimum, or even a plateau that we quite often encounter in protein purification. And then at the very end of this long transfer function, we have that little e term, which might look nondescript, but is very important. And again, that's the prediction error for the model and what captures all the random variation in our process that we cannot understand or cannot quantify as depending on one of the process inputs. So a simple cartoon of what a two-factor interaction effect can look like. On the left-hand side, we have a scenario where we do not have an interaction between the x1 and x2 parameter. So the graph is y versus x1, and the blue line is how x1 affects the y at a low setting for the x2 parameter. The red line shows the same effect from x1, but at a high setting for the second process input, the x2 parameter. And as you can see, the slope for these two lines are the same. So the effect that x1 has is the same regardless of how we set our x2 parameter. In that scenario, we do not have an interaction effect. On the right-hand cartoon, we have an interaction effect. And here you can clearly see that the slope for the two lines are different. So this means that the x1 parameter has an effect on y that depends on the setting of the second x parameter, the x2 parameter. So if x2 has a high setting, so we're following the red line, you'll see that the x1 has a lot less effect, a lot less impact on the response than if the x2 parameter is set to a low setting. So this is a real-life example of an interaction effect from a aggregate removal chromatography step. We're here looking at how pH and conductivity affect the aggregate removal. So the colors here represent the amount of aggregates we have after the step, the unit operation. Blue being a low amount of aggregates, red being a high amount of aggregates, and the other colors going from low to high down. And here you can see that if we start, for instance, from the bottom left corner at the low conductivity and the low pH, and we gradually increase the pH, holding the conductivity constant, we'll see virtually no effect from pH on aggregate content. So we can basically choose any pH we like and still have a good low amount of aggregates. However, if we increase the conductivity, so let's say we move to the top left corner, now you see that we are no longer free to choose any pH we like if we want to remain in the lower ranges of blue and of the bluish colors. So now at the high conductivity, pH has a drastic effect on the aggregate amount. The inverse holds as well. if we choose a low pH, so starting again from the bottom left corner, if we have a low pH and we increase the conductivity, you'll see a drastic effect on conductivity. So we cannot increase the conductivity from a low pH and still have a low amount of aggregates. However, if the pH is set high, we can safely increase the conductivity and have a good aggregate removal. So the pH and the conductivity interact in terms of how they affect the aggregate removal for this unit operation. And in downstream processing, with charged proteins and resins that interact with those charges, and also hydrophobic and other kinds of interaction effects are quite common. So it's extremely useful to employ an experimental approach that allows one to both detect interaction effects and also to quantify them, so that we can design our processes to take maximum benefit of these interaction effects. So in addition to what we can quantify in terms of interactions and so on, and the polynomials we use, we always run a number of center points. Why do we do that in DoE? Well, first off, since the center point, the center of our design probably is the point we're most interested in, of course we want to run experiments there. But in addition, we repeat them a number of times. We repeat the center points to give us information on the repetition or the replication variation of our process. So remember that all the other corner points of an experimental design are typically only performed once. So we have no reproducibility for the process outside of the replicated center points. I mean, typically we do not replicate the corner points. We can do that, but typically we replicate the center points. So by replicating the center points, and by replication we mean repeating the experiment all the way from start to finish, including new buffers, new column packings, everything new. We replicate the whole experiment. By replicating the center points, we get very valuable information about the process variation in itself. And this is highly useful when we then, as a comparison to the model prediction error. You remember the error term we talked about? So at one of the key statistical tests in DoE evaluation that we'll talk about in the next part of this presentation is going to be comparing the replication variation to the residual variation. So that gives us information on whether or not our error term is in agreement or not with the process replication variation. The second reason for having center points included is that by having those, we can identify if we have a second degree curvature in our process or not. So this is different from interaction effects. This is talking about if we have a plateau or a maximum or a minimum in our process, in our investigated process space. So if we have center points and we employ a DoE, an experimental design that only supports the linear model without quadratics, well, if we have center points, we can see if that's enough or not. So if the center points are well described by a linear model, then we know for a fact that we do not have a curvature behavior in our process. However, if the center points do not fit to a linear model, then we know it's worthwhile to expand and extend the experimental design with those experimental points that will enable us to fit a quadratic model. So if time and or sample amount is of the essence, we may opt for going for a linear model and an experimental design that only supports a linear model first, see if the center points fit to that model. In that case, we're done. If they do not fit to the model, we know it's worthwhile to expand the experimental design with second degree curvature and the experiments to support that. One note here about verification and validation of DoE models. Of course, statistics is very important. However, statistics only go so far. It's very important that our DOE model and the transfer functions we develop in DOE also make mechanistic sense. So whatever model we decide to run with and arrive at should be fully interpretable. And we have a number of evaluation tools to help us do that interpretation, to see that what the statistics are telling us about how our process works really makes sense from a domain knowledge perspective. We can also, so that's talking about the f of x part and saying that whatever quantified effects we have, they actually make sense. Also about the error term and the residual terms, that's also something that we can assess from a mechanistic perspective. So the residual standard deviation, the amount of variation that the model cannot explain, we can immediately compare that to our measurement system error. Typically we know how much variation we have in a purity assay or in a yield determination or so and so on. So naturally, a predictive DOE model wouldn't be expected to come in with a much better, a much smaller prediction error than the analytics that we employed for measuring the Y, right? If the error terms come in much lower, probably we have overfitted the model and it's not really so statistically sound as one might have thought. Second part would be, again, comparing to the measurement system error, the analytics. If our model is hugely less certain about its predictions, so meaning has a much larger error term than the analytics, that's an early indication that something is going on in the process that we might need to understand better. So that's when we evaluate the model, it should make mechanistical sense. Then once the model is developed and seems to be working fine, a very important follow-up to that is, of course, how well does our optimized and refined DOE model, how well does it predict new experiments? This can be verifying runs in the same lab scale, same equipment and everything. Could be a starting point. It can be predicting the next level scale up to the pilot scale. Can our optimized lab model successfully predict the next scale? Fingers crossed it will be able to do that. And typically if care and caution is taken, it does work extremely well, especially in chromatography, which is so beautifully scalable. And of course, that validation and verification of a DOE model is a very strong evidence that we have a sound and working DOE model. So now we'll look at some different examples of experimental designs typically employed in DOE. First out are the full factorial designs, which are often used if we are studying a very low number of process inputs or X parameters. So if we are at 2 or 3 or 4 parameters, then we would turn to a full factorial DOE. Full factorial designs employ combinations of all combinations of the high settings and the low settings between all of the process X's that we study. So if we have 2 factors, we make a 4-corner square. If we look at 3 X factors, we perform the corner points of a 3-dimensional cube. 4 would be 16 corners, and then the list goes quickly up. So for 7 process inputs, if we would employ a full factorial DOE, we would need to run 128 experiments, because that's the number of corner points in a 7-dimensional hypercube. So that's a little bit or significant bit of overkill for quantifying linear effects and interactions, 2-factor interactions, which is where we normally stop in DOE, experimental DOE. So when we study more than 4 or 5 factors, or 5 and above, we have the option of turning to fractional factorial designs instead. So the cartoon here looks a little bit complicated, but it's actually rather straightforward in my view, at least. On the inner cartoon here, the inner square has the x1 and x2 parameters from low to high. And then in each of the corners of the inner square, we have x factors x3, x4, and x5. So we're looking at a 5-dimensional hypercube, which would then, in a full factorial, it has 32 corner points. However, if we are interested in the linear effects and the two-way interactions, it's actually enough to perform a systematic selection of only 16 of the 32 corner points and get a solid support for linear effects and two-factor interactions. So by taking that fraction of the full factorial, we can have a good support for the DoE polynomial with linears and interactions. A design of this kind that supports the two-factor interactions is called a resolution 5 design. And if we're able to run a resolution 5 DoE, that's very good. However, if we want also to have support for the second-degree terms in the polynomial, so the full response surface modeling polynomial, linear effects, two-way interaction effects, and a second-degree curvature, we need also to add some experiments to quantify that curvature. When we add those experiments to a factorial design, either a full factorial or a fractional resolution 5 factorial, we get what is called a central composite design. Cartoon on the left shows a central composite circumscribed cartoon where you can see the full factorial square here in two dimensions. Those would be our DoE corner points, and in addition we have added star points going through the center point. So we have one experiment here, center point, and one experiment here, where only the left to right process X is changing. So depending on the process output, then if it's linear, those three results that we get in from here to here to here will fall in a straight line. If we have a plateau or a minimum or a maximum, those results will describe that for the model or for the evaluation. And we have another unique direction going top to bottom where only that direction is changing, which enables quantification of the second degree curvature in this direction. We can another alternative to make a central composite design is to put the star points, the so-called star points, on the face of the square instead of on a circumscribed sphere, which is also an option in experimental DoE. With more than 4 or 5 x's, however, it's good, if it's possible, it's good to put the star point slightly outside of the factorial parts, high and low levels. And this third cartoon is the central composite circumscribed in 3 dimensions. So the factorial part can be either full factorial or resolution 5 factorial, and then we add experiments 2 and 2 to be able to quantify the second degree curvature as well. So finally, an often asked questions when we sit down and discuss how and when and why to run an experimental design is how many runs will it take? How many experiments do we need to do? This table addresses that question, and the question is, the answer to the question is that it really depends on what level of complexity do we need to understand our process at, or what level of polynomial complexity support do we require from our experiments. If we are in early phase stages, only we are screening or we are robustness testing our process, either in the early phases or the very late phases, we would be happy with complexity in the top here, with only a linear model would be okay, because we're not really looking to make a detailed predictive model. So we would be at resolution 3 or 4 in factorial designs, and you can see that then we can study quite a large number of process inputs in only a few experiments, relatively seen very few experiments. And of course this table goes on. You could say that if we perform a 16-run fractional factorial, we could study as much as 15 process inputs. So very useful for screening large number of parameters or robustness testing a large number of parameters. However, if we want to really quantify the cause and effect, and we have a process that exhibits interaction effects or second degree curvature, which is often the case, especially in downstream processing, we would expect the linear model not to be enough, but we would need to go down to either a resolution 5 or full factorial, to enable us to describe also the interaction effects between our process inputs, or even to a response surface modeling DoE to also enable us to describe a plateau or a maximum minimum. And naturally, the number of experiments we need to run increases. So you can see if we are studying 7 parameters in detail, we are looking at somewhere around 40 experiments or higher to make an RSM DoE. Therefore, that's why it's so valuable if we are able to screen and, based on our previous knowledge, select the really critical X's that we need to describe and study in more detail, so we can move down to maybe 4 or 5 X's that we do an RSM DoE on. But of course, this depends on the individual application, on the individual process, how many critical X's we really have. So that concludes the first part of this three-part lecture. Thank you so much for listening in today, and we will continue in the next part with looking at the evaluation of DoE data. Thank you so much.